Good day and welcome to GMAW, that's Gas Metal Arc Welding Discrepancies, Discontinuities, and Defects. I'm going to be your host for the next couple of hours. My name is Bob Bosworth. I'm the president and CTO of Elite Welding Solutions. Now, we have a whole bunch of things to cover today, but let's start off by identifying exactly what we're going to be doing. So, today we're going to talk about welding. We've already talked at this point. You will have already been through the gas metal arc welding program, and you most likely have some experience at what you've done. So what we're going to do is we're going to focus in this program about discrepancies and defects and discontinuities, and we're going to go through all the different phases that go along with it. But we're not going to stop without having a talk about what to do, what your responsibilities are, because that's the key figure of this entire presentation, is going to be your connection with the quality process. And I can't stress that enough. So then we're going to talk about visual inspection. What's your expectations? What is the company's expectation of you when you're standing there at that booth and you're defining whether or not a weld is good or bad? And furthermore, this is all about defining your skill sets as well. When the OEMs show up and they want to know how does that person know these welds are good or bad? Show me the training that these people are under to define whether my welds are good or bad. We're creating that documentation process and that skill set within you at these programs. Off-location welds. What to do about an off-location weld? Where it happens, what it looks like. There's going to be a whole pile of pictures coming your way. Visible weld porosity. This is a big deal in the automotive industry right now because one of the most popular things to do from the OEMs is to put zinc galvanizing all over steel. The zinc galvanizing causes a lot of porosity, and it's a constant struggle to try to stay on top of it. Burn through of base metals is going to be discussed. That is when there's a big hole and we got to do something about it. Undercut of base metal. We'll get to that, and we'll talk about that in some fair detail because I consider it to be, and many consider it to be, in a dynamically loaded, that is a structure that's constantly moving, it's considered to be a very serious defect. So, stops and start issues, cracking, spatter, and then we'll have a little bit of a technique review. So, if we can just carry on from here, it all sounds good. Now, first thing we kind of got to talk about with all this is let's talk about the trained and capable person. This part of the process that you're using right now. The trained and capable person is a person that can see okay. They've validated their eyesight. They have been trained to define between what defects are and what should happen when they see something that is discrepant. So you're getting ready to inspect something. So let's define first that these inspections should happen without the aid of magnification. Magnification would slow the entire process down, and the OEMs recognize that things have to move at a very fast pace when it comes to inspecting and defining whether a weld's good or bad. That's why we'll sometimes have multiple inspection stations, inspection points even, where we define whether or not this is good or bad and should it carry on in the process or should we stop the whole line. There's a bunch of things, but you shouldn't have to get on top of a weld. You should be able to inspect the weld from pretty much arm's length. If you held your hand out in front of you and stuck your thumb out, you should be able to inspect something from that far away. And going back to your eyesight, that's the important aspect of it. So, you've looked at it. Whoops, it's a discrepant weld. The discrepancy means there's something unusual about it. Is it good? Is it bad? Does it meet the specifications? So that's when this turns into a moment of choice. Is this weld a discontinuity? The weld has some areas in it that have what we will clearly define later as defects, but they're below the limitation. Right? One of the common ones, we haven't discussed it yet, is porosity, the size of a hole in porosity. It makes weld look like a little bit like Swiss cheese if you've never seen it before. But these limitations, they give us the grounds to say, yes, that's okay and that's not. We're not selling them a perfect part. We're selling them a part that complies with the specification. So if you have a situation where you have a discontinuity, and this discontinuity that you see is below the limitations, that's what makes the defect a discontinuity. It's below it. So now this is a discontinuity. It does not need repairing. The next one is the defect. Now, for example, if there's that porosity where there's holes in the weld, little visible holes, there might be a lot of those holes and they might be very, very close together. If they go beyond that, it requires a repair. If they go beyond what the OEM specification says. And we will discuss what that specification generally says later on. So again, we go from the trained and capable person, without the aid of magnification, inspects a weld and sees it to be discrepant. In some way, you're curious about it. You have to make a choice, and it's very quick. Is this a discontinuity? It's okay. It's a very small defect, so it makes the entire weld, looking at the entire weld, a discontinuity. Or is it a defect? We have to effect the repair right here, right now. Always remember one thing, if you may. You guys, you all are inspectors before you're welders. If you want to be good at this job, you have to become very good at understanding what to fix. Remember, you're not welders first. I don't want you standing there welding or thinking you have to be welding to have that job. There's no way to be there to make this type of contact, but I want everybody to understand how important it is, how important your job is. That you make sure that these machines do what they're supposed to do. And you are our eyes and ears, from engineering to quality, and I think I can speak from every general manager all the way down to where we're building the parts, that we're counting on you to pay attention. So inside of plants, there's a bunch of different things to consider. Sometimes inspection stations are actually happen inside of the welding process. Sometimes the inspections happen what we call offline. Now, I want to have a quick word because I've been involved with probably over 20 serious recalls over my career. And within that period, almost every one of them happened as a result of poor tagging on the shop floor. So I know that's not what this course is all about. It's not about tagging, but I want to throw my 2 cents worth in to make sure everybody understands that it's very serious. To make sure when you've got parts that have to move from one station to another, especially when they do offline repairs, you have a new problem on your hands if you do not put label these or use the correct tags in a proper form. Now, every plant's going to have their own way. I have ways that I consider that I like, but make sure you respect what goes on inside your plant. I go to hardly any plants that don't have a good system in place. It's all about your diligence, your personal diligence at that moment to make sure everything is done correctly. Now, one of the things we do for understanding defects, discontinuities and defects, is understanding whether you have border samples or not. Now, there's a whole bunch of reasons to use these. And the border sample references might tell you or help you to understand what a good or bad weld is. Now, not every plant have them, not everybody wants to use them, but often we'll make up a whole bunch of welding samples, and we use these for training as well. And the border samples can help you to define whether a weld is good or bad, and that is over, above, and beyond what this training program can do. Now, this will help you make some of those decisions. Now, other issues to go with this non-conformances, we've had labeling issues, identification of parts. There shouldn't be anything that's left on a tag that you inside of your company that's left blank. Because as soon as it's blank, it leads to an assumption. An assumption, I think we've all heard the expression about assumptions, right? And make sure leadership understands. So let's talk about the weld itself for a few minutes and the attributes of a weld. So here we have a weld, and it has the first and foremost when it comes to a weld is this dimension and structure. So let's talk about dimension for a second. There is nobody that's going to ever expect you as a welding inspector, which is your primary goal, that's ever going to expect you to look at a weld and start to use what the gauges or the devices that we use to measure the dimensions of a weld. There's nobody that's going to ever do that to you. What we will do for you is we will provide you samples, sometimes, as in the previous slide, in the form of a border sample that says this is a good weld and this is a bad weld. It gets us to a good place where you can make that visual determination. In fact, if you're standing there and the OEM, whoever, Chrysler, Ford, whoever, walks up and says, "Hi, I'm from Ford. How do you know that that size of weld is okay?" It's quite a common thing during an inspection to have a couple of words with someone. And your answer would be, "I have a comparison sample. I have a part that I can go to learn about this part." And when it comes to the actual size of the fillet that we're discussing, I just compare that part to this part. And that would be the correct answer. He wants to know that there's something there. Now, this puts the onus on quality and engineering to make sure that there's a part there for you to see and to use to make this determination. Now, the structure of a weld represents, of course, different shapes and sizes inside the weld. We're going to identify those very soon. There's actually a whole bunch of terms I want you to know that goes all around this thing. And the second part to a weld, the two basic, the fundamental things is the penetration. I want everybody to understand that all these MIG welds, and we've heard of the term MIG welding. That's the proper term is gas metal arc welding, and this is the weld metal. You need to understand that this metal is not the same as this metal. We don't match these up when it comes to steels. The welded materials are much different. They're much different in metallurgy than the base metals. And what it counts on, we are actually counting on penetration from this material, all this penetration, to homogenize, that is to mix with, to homogenize with the weld and give it the strength that we need. So my point here is we qualify these. You as a visual inspector, you look down at the weld and you're looking at the things that you can see. There's things that happen in front of what you do that I want you to be aware of. So if I can, the first thing I always want you to do is to make sure, and there'll be more information on this later, is to make sure that when you see a wire being changed on a machine for you, I want you to make sure that that machine gets the same type of wire put back on. Whether you do it or not, you read the label. Because there are a lot of mistakes that happen because somebody goes to the crib and gets some wire from and they see MIG wire, they grab it, and they put it on, and it might be the wrong one. And certain materials will start to crack if they're not welded in a certain method. So we do a lot of work out in front to make sure that you have the correct metallurgy, like the wire that we've determined. Well, they call this procedure when we're developing procedure. The correct metallurgy, the correct amount of heat input, that is the parameters of the weld to give us penetration. And then, of course, we teach you technique, how to do it. So my point is this. You don't have a lot of discrepancy. A lot of people believe as welding people that, okay, now I can start playing with the machine. You don't. You don't get that option because we report how we do this and we need to execute how we do this. And if the customer had a problem, he could walk right in and walk right up to your machine, and we will have provided him parameters for that machine. And if they're not right, there's going to be a discussion, a whole bunch of them. So let's have a talk about the welds themselves for a second, because the fillet weld is your very basic weld I've been showing you all along. And your basic fillet weld has a bunch of pieces and components. And I'm going to talk about these over the next probably half hour or so. And let's make sure we understand what these are. So the first part I want to talk about is the toe. And they actually have a horizontal toe, a vertical toe and a horizontal toe. Now the toe represents that area right there that interfaces between the base metal and the weld metal. Now, this whole area is of very serious interest to metallurgy, the metallurgy side of the weld anyway, but we're always interested in that area because sometimes we'll see a lax of fusion going down here. We'll see a weld from one place to the other, but either way, the toes tell me, as a CSA visual inspector, that the toes are the gateway into understanding the heat input. How much of a bump is on this weld and how the material flows into the other one tells me a lot about how much penetration we actually have. Because we actually need, as I was talking before about this homogeneous mixture in this area to give the weld the extra strength that it needs. Not to mention, it gives it more fortitude. The deeper we can go into the base metal, to a certain extent, the more strength we'll end up having. Now, the face of the weld is what you see. So far, everything we've talked about, you see when you're a visual inspector. So the face of the weld can tell you if there's cracks. The face of the weld could show you porosity. The face of the weld can tell you the shape of this weld. There's a special name for this shape. I'll talk about it later. So there's a lot of things it can tell you from looking at the face. Now, that's it. After the face, you've done everything you can do as a visual inspector. The rest of the stuff, engineering and quality did it. Engineering and quality design were the ones that said, okay, if we have a leg length that's 3 millimeters, then 0.7 times that should be the throat. And they're the ones that worked out all this other stuff. You'll be given instructions in your workstation that will really help you with these. You should be given instructions anyway. Now, the effective throat takes this theoretical throat, when we drop between the toes and down like this. The effective throat adds the penetration zone to it. If we're adding the penetration zone to it, now it's working out very well, especially if we've met the criteria of making sure we have a full root. Now, next one's the vertical leg and the horizontal leg. This is the most common version of looking at the leg length. There's all kinds of extra specs when it comes to groove welds, far more advanced, but it's always makes good reading. But the leg length is very common in fillet welds because it's very easy to measure, and it's easy for us to deal with them from a quality perspective when we have to do destructive testing. And the last one is about this bump. It's something called reinforcement. Now, some specifications from OEMs, original equipment manufacturers, they don't define the reinforcement at all, and some limit it. The Canadian Standards Association, the CSA, which sets aside all the rules and standards for the CWB to do their job, they limit reinforcement when it comes to structural welds because they know the bigger this bump is, the more stress we end up developing in these areas. So there are some limitations. Remember, these things have already been taken into consideration. All I'm asking you to know right now is if we're talking about a toe, I would expect you to know where the vertical toe is, the horizontal toe, and of course, all these other parts. Now I want to talk about what you do inside of a cell. What is mine and your bosses and everybody else's expectations when you step into a welding cell? So, I'm going to tell you these things based on my walk-arounds with OEMs over the past 20 years. The types of things they look for, and I've basically put the things that they've said to me down on paper, and I wanted to share them with you because I can't say anybody's going to do any of this, but at one point or another, everybody has and it usually hasn't happened as a result of a trip-up because we weren't ready for them. So, first thing, work safely. They all have on their check sheets something that says, does this area look safe? Does it look like we've done our due diligence in making sure that the worker is safe? Because remember, almost under all conditions, If you're standing with Ford, Ford owns that cell. They've bought it off. And under those circumstances, this piece of equipment is actually theirs. And they're thinking about it that way as well. And after that, they would have expectations that when you put somebody on their equipment, that person would be using the proper personal protective equipment in all forms. Next one, be prepared. So one of the things I'm going to do to you is I'm going to tell you that they're going to expect you to be prepared. Do you have your tools? So you've got your safe, you've got your whatever you have to wear, and whatever's been deemed necessary in your plant, your PPE has been provided to you. So what being prepared is, do you have other things now? Are you prepared to do the work? Here's a great example. I went to a large plant many years ago, and I was actually conducting this particular audit, and I walked up to a fella, and I was being supervised by the plant. They were watching me, and I walked up to one of the reprocess guys, who was clearly, by the way, a very good reprocess welder. He could act quickly. He could act quickly to inspect. He executed the weld, but when it was time to weld, he was very calm and did a good repair. But I asked him, I said, so if you see porosity, what do you do? And he said to me, he was properly trained, because he said to me, porosity that does not meet the specification requires grinding. And I said, that's a fantastic answer. I said, do me a favor. Get me a grinder. Show me the grinder. And it took him 15 minutes to find me a grinder. You'll never convince an inspector that you are doing something if it's not readily available to you, because there's no way you're taking 15 minutes to go find a grinder. The truth is, the gentleman knew the right answer, and he even understood the right answer, but he was not prepared. And then there's a bunch of other things too. If there's spatter-free zones, we got to make sure you have something to scrape those zones and check those zones. There should be information there for the if there was spatter-free zones, where are those spatter-free zones? How clean do they need to be? These are all things that can be done for you. Then now you've got your working safe. Now you got all your tools. Now your job, the robot presents you with a nice component to inspect, and then that component gets inspected by you. Now, here's an important moment. I ask one question. There's a question I ask when I do inspections, because of a gentleman that actually worked for Chrysler, who I dearly respected. He used to ask this question, and it was the greatest question ever of a person that's working in a reprocess cell. And the question was, how many welds do you inspect at this cell? So the question always turned into, when we got back in the office later on, if the person gave the right answer, great, the whole thing was dropped. If the person gave the wrong answer, the impression is, if there was one weld missing, the person wouldn't know it. There would be a gap. There would be welds missing from this part, and we wouldn't know it. So we want to give the right impression that you know how many welds you should be inspecting on this cell. Now, this information, again, is either you've got it by what your station is supposed to inspect, and you know what that number is, or in most cases, if weld instructions or work instructions for that cell are available, it would be a great big number in the top right-hand corner of every one of the and it is in every one of the work instructions that I do, because I think it's an important thing to know how many welds are supposed to be here. Next, determine if they meet the specification, right? We have a look at those discrepant areas, and we decide overall, does this weld have a discontinuity in it, and it's okay, or does it have defects in it that meet or exceed what we were talking about before, meet or exceed the specification? And if it's yes, you stand back and you swipe, or you take that part and you put it in a good bin. It's up to you. It's up to you. That was your choice based on what you've seen. If no, Now your welding skills come into place. We need to execute a reprocess weld and bring it up to a specific place. So, as a welding inspector, you will understand and have to understand that size. Here's a rudimentary picture, of course, of a weld that's a little bit off location, but very likely to what you would see. I'm actually going to show some pictures later to show those off location welds, and it looks a lot like this. But off location welds are very good because they're clean. There's no porosity or anything else that has to be ground. Simply putting another weld in place is a very simple and easy way to bring this leg length back into where it's supposed to be. And that's the whole idea. We have to have good contact with a certain amount of distance. So that would do it for us. So here's a good example of something I've done, and this could be a part of this presentation that's more for engineering and quality than the people that are performing the work. But you guys need to know about this device too. So as the people performing the work, you need guidelines for what this component should do. So this is very typical of the organization of how to identify what welds are where. Now within this engine cradle, this is the engine cradle RU, Chrysler Pacifica. So within this engine cradle, there's a whole bunch of welds, and what we've done is we've identified them. By the weld number, you know what side they come from. And the right hand's even, and the left hand is always odd. So you know what side they come from. You can identify certain things. There's mins and maxes for welds. And let me just say this at this point. The size of the weld and all that stuff, that's all your responsibility. The length of the weld is not. Length of weld audit should be carried out by robotic people who are in control of those lengths. Right? And here's another very important tidbit that goes across the board for almost everything. You never put weld metal where weld metal's not supposed to be. Ever, ever, ever. There are changes, structural, metallurgical, and strength changes that happen to these materials when they get hot. And you putting welds or thinking, oh, more is better, and I'm just going to take these two welds and connect them together. No. Always remember something in behind all of this. One day, this component might be subject to crash tests, not just in testing, but in the field. One of the things they have to do, and one of the things that engine cradles have done for us over the years, is greatly increase the safety of a vehicle, because it gives our bodies more time to decelerate, how it crushes, how they want the engine to roll and end up underneath your feet. So there's a whole bunch of technology behind this. Your expectation is you're going to put that weld exactly where you're supposed to put the weld based on what these samples say. Now, that being said, if you ever see one of these that are exceptionally long, and somebody's got carried away with the weld length, right, it would be good to report it and point out the fact that on the test, on the sample piece, right, you can call this a border sample if you wanted to, not exactly the idea, but on the sample piece you have for inspection, that a weld is much longer. Longer or shorter, both of them could have dire consequences. So we talked a little bit about off-location welds and how to put them back to where they're supposed to be. Here's a good example here of an off-location. And what happens is with the gas metal process, there's a liquid. We talked about this liquid and puddle in previous presentations, but it's a liquid. And one liquid, always remember this, liquids love liquids. You take two puddles and connect them together. It's the same idea. But if this side becomes more liquefied than this side, it tends to drag the material up towards that liquefied section. So it's a very common thing that can happen with ever so slight fit-up issues, where the weld metal just has to kind of pick a side. It picks the side that has the most liquid and is drawn towards it. Simply by you effecting a repair like this and putting it in place, you will have restored that leg length to where it's supposed to be. Visible porosity requires some discussion because it's a pretty serious problem. Now, almost always the serious issues we have with porosity and the challenge, I should say, we have with meeting some of the specifications is a result of zinc and zinc vapor. So years ago, there were some challenges with making sure that we have corrosion resistance with the thinner materials. This was a result that thinner materials were required to save weight, but just a little bit of rust on a thinner piece of material had more consequences on crash test development. So everybody decided pretty much that they're going to start throwing zinc all over all the steel. And this is just basic, mild steel, under most cases, a basic, mild class steels, but they actually put this coating of zinc on top, which absolutely will not rust under these conditions. So we have to weld through the zinc. Now this is a whole different course to go about how to go about and what's the process of developing procedures that can weld through zinc vapor. But know this, if in your welding process, the zinc, and this is all thick zinc that's right in here, if the zinc gets caught inside this puddle, it can't get out and it will not mix with the welding puddle. So when it doesn't mix, zinc actually boils inside the iron of the steel. It boils inside of it, creates a gas when it creates that gas, and the gas is captured while the weld material is starting to solidify. So zinc is a very serious issue. We're going to talk about the porosity standards in a second. Now you can have porosity without it. If you don't have adequate shielding gas coverage, remember from previous presentations, we have to displace all the air that's around it. And sometimes we've got a compromised flow of the gas. Sometimes we've lost gas. There's a bunch of different reasons for having it. Simply having too much oil, there's a pile of reasons why you might have some level of contamination for porosity. My criterion for porosity when you see it is stop, especially if it's anywhere near the spec. Stop, clean the nozzle. Make sure the nozzle's nice and clean, and then start again. Now and observe. There's a bunch of reasons why you might continue to get it, but let's make sure we've got a clean nozzle first. The spatter will sometimes go up inside the nozzle and cause disruptions in the gas that cause those issues. But I always say, step one, clean your nozzle, keep going, observe. So porosity has limitations. Now I want everybody to understand that there's a size that you're allowed to be at, and that's 1/16. Now, this is a great time to bring up your eyesight because you got to ask yourself, can I see a pinhead, which is about a pinhead, which is about a 1/16 of diameter from arm's length? Because that's kind of what you're doing. I don't want you, nobody wants you working harder than you need to. A visual check just means when you see a cluster of welds, you should be looking at them from a comfortable arm's length. You shouldn't be performing calisthenics or gymnastics trying to figure out where all these welds are to look at them. This is a glance, an educated, observant glance looking for discrepant welds. So once you have discrepant weld, whoop, what's different about that? Now it's time to define whether or not it is just the weld overall just has a discontinuity, or do the discontinuities keep adding up until the point we have a defect? Okay, so within the standard, it always says 1/16. Now, I don't know a standard that allows anything bigger than 1/16. I know standards that say they allow nothing, but there's a lot of conditions that go around that. And very, very seldom do they ever come up. Now, I want you to understand some of the key points, because one of the most important elements inside of almost everybody's porosity limits is understanding how much porosity there is inside of an inch or 25.4 millimeters, and they'll give these different distances. So I want you to understand the flavor, if you will, of the spec by looking at the first one. So the first one represents two holes that are 1/16 in diameter. Now these 1/16 holes have a space in the middle of them that has 1/16 of space, right there. Because of that, because it's 1/16 is the maximum, so we're just there around a 16th. We've got a gap. Overall, this would be a successful analysis because we've said it's okay. There's a gap between the two of them that's separated. Now, would you actually leave it? Might you let 2 1/16ths go through? Yeah, you might. But most people would take a grinder, touch it with a grinder, because porosity cannot be just welded over. Now, there's going to be people in that room, right there, right now, who have decided many years ago, maybe you've been doing this for decades, that when you see porosity, you just weld over it. I want you to know one thing. It's not gone. Yes, you've made it disappear. I get it. And the customers would prefer for their e-coat conditions to make sure that there's as few as possible. Remember, e-coating is less than effective if you can't get the paint all the way down inside the holes, and it's very difficult to get it all the way down inside these porosity holes. So they prefer them not being there. But you cannot just weld over it. And just so you know, if something happens in the field or something happens at the plant where we have to go do a test, we know. We'll know if you welded over it or not. You'll be able to see both welds very clearly, the first weld and the second weld. And that's when, from my perspective, we really get in trouble. So, next, of course, it's not going to be acceptable because now you're getting a string. Sometimes you'll see this show up, and here's a little picture down here at the bottom. Sometimes you'll see this show up, and it's a result of so much porosity down at the base of the weld. Right? Again, here's a good time to refresh on this. If you're welding too fast, and that's one of the things the robots do, is the robots go fast enough that they can go quick enough that they'll ride on top of the steel and let zinc get into the puddle down at the bottom. When that happens, the zinc boils, trapped gases expand, and we have porosity. Now the last one should be fine. We have a few small bits here and there. The specifications are clear, what's allowed and what's not allowed. And once you get well below a 16th, even if you have a cluster, remember it's the diameter separated by itself, not a 16th. So if it's a small little diameter, you've got a lot of room to move here. Okay, here we go. I want to mention this because I've seen it so many times. This is the inside of a gun that was reamed about 10 parts ago. And that is, there's a reamer. The robotic guns have a reamer that when the gun comes over, it clamps it, goes up and cleans the inside out. Sometimes it'll shoot a little bit. The really good ones will shoot a little bit of air out to make sure it blows all the junk out. And most of them just do the ream, let the stuff fall out, and then send it over, and it puts a little bit of spray on it that both cools and coats the nozzle a little bit so spatter doesn't stick to it as easily. But I want everybody to note right here, see these clusters that build up inside of nozzles? We have a situation, and I've had too many of these calls, and I wanted to put it in a presentation, and I call it, for lack of a better word, phantom porosity. So I see this in cells where the guns run a long time, or sometimes a longer time between reaming cycles than they should. And somebody will report, and the stations will report, porosity that comes and goes. And it'll be over here and over there. It's in no specific place. Now that's key for me when they say I'm getting porosity now and then in no specific place. And what I'll always say is, and I'm telling you this as possibly robotic people, but definitely people that are going to be some of the first people to lay your eyes on a weld. I'm telling you this because I need you to start paying attention to, when you see this, start paying attention to when the robot reams and this porosity. Because if this porosity shows up at the last 2 cycles of your cycle between reaming, If it's the last 2 cycles and then it goes away immediately after it goes for a ream, this is the problem. This happens so often, I really needed to make sure I bring it out there. But it does lend to the people who do the actual welding. You got to make sure you keep your gun clean. You don't have a reaming station. It would be kind of cool, but you don't have a reaming station. You've got to keep your gun cleaned up manually. Burn through. Burn through that's one of the best pictures I've ever seen. I took that in Mexico a few years ago. It actually has a couple of other lessons buried inside of it. Look how much greater the heat input is in the steel, and because the heat is dumping out of the weld into the material around it. Over here we lost location, and this happens. This is going to happen to you guys anyway. This happens, and once it collapses, the heat input, hardly anything. All the way out here, hardly anything at all, because there's no weld metal to push it into the materials around it. We call this heat affected zone, and it also could be defined inside of understanding what penetration is. There's clearly good penetration here. Now, burn through is caused by excessive heat. You're going to see this. Now, as a welding inspector, your job is to look at this and go, okay, there is burn through here. Now, I do not want to go deeper than what I'm about to say, but whether or not a part can be welded or repaired that has burn through is completely based on the spec, your welding engineer, and your quality department. So that needs to be defined, because some parts can be fixed and some parts aren't. And it has to do with the classification of the weld. And we're going to talk about those classifications, that classification really, really soon. Here's another good example. Now this is a part that can be repaired. So there is an opportunity. There was an opportunity here to have this small hole where they've had some burn through. And in this particular case, this company had opted to put a small piece of copper behind the weld. Now, there's an idea. It's a thought, and it seems like a great way. Put a piece of copper down behind, and then try to weld from this top side. Here's the problem. There's going to be some junk hanging down on the other side, and it's going to have a grinder put to it. Now, I want to talk just momentarily here about grinding, because it's an important aspect. If you use a grinder on a part, you don't hit anything but the parts that are supposed to be hit. And that is, not a buffing disc, not just taking a little bit of the spatter off. If you're cleaning like that, that's different. But if you take a grinder with a hard disc that is meant to remove material, you have to stay away from all, especially this zinc coating, because if you bump into that, you thin it out for one, and you remove the zinc coating for another. And we don't want either one of those things to happen. So, welds have classifications. I'm going to give you a quick overview of this from an engineering perspective. But welds have classification based on their utility in the product. Some welds have to be perfect. Everything so much relies on that particular weld. It's everything's in this. There's 10 welds here, and as long as these 3 are perfect, everything's fine. So in engineering, they look at these welds and they find out which ones, and they do extensive testing to find out sometimes which ones have the problem. And they will say that welds become safety welds. They use classifications for welds. There's different types, right? Now, this is kind of old school, but this was a symbol we used to use that represented a safety weld. When you seen this symbol on an engineering drawing, it means this weld needs to be nothing less than perfect. It has to have no porosity. It has to have proper penetration. And here's the other thing. It can't have any repairs. It can't have any stops and starts inside of a certain area. You see this often now where they want a weld to start at one place and end at another, and they don't want an interruption between them. And they call it out for us when we're looking at engineering drawings of these components. Now, the safety weld, or however your company defines, if they're not as old as I am, they use the classifications, but they basically define whether or not you can actually do any repairs. Now, on your information sheet, which I'm going to show you an example of one very soon, but on your information sheet for working on that product, the safety weld information would be there. And if I could put my hat on again as the welding inspector who's looking at this, if I could put that hat on again, I would say, if I looked up and saw that symbol or saw there was a classifications for the welds, it was class 1 welds, I might ask, which one of these are safety welds? And you would need to understand that, and you would say, oh, this one, and this one. And remember before, and this is probably for engineering and quality, before there was, I showed you an engine cradle, and it was all marked out. That had 6 safety welds on it, and I identified those safety welds. And everybody who worked in those cells also had more bulletins about, these welds cannot be interrupted. These welds can't have this problem. And they were struggling and crash with a particular area. Now, welding instructions could take a lot of discussion, a lot of development, and a lot of time. Not everybody has component welding instructions. This is one of the things that I do, is I come into plants and help develop your procedure and populate these reprocess sheets to make sure the reprocess station has everything they need to do, every bit of information they need to do a proper inspection, to know exactly what needs to be done. And basically you put these up and you get them correct, and usually you don't end up with a whole bunch of bulletins beside it because everybody understands. It's also a training spot. This is where somebody's walking up to this area, and he could be the best welder in the place and the best inspector in the place. Without the information he needs to do this, it's not going to happen. He's not going to. He's just going to be able to. And I actually don't like people that classify a welder as just a trigger man. Pull the trigger and get it done. You know what? People that just pull the trigger every time, they cost a lot of money. And they can do more damage and do more harm to a part than understanding exactly what the spec's supposed to be. Undercut. Now, undercut is pretty simple. What's happened is the heat, for whatever reason, and there's a bunch of them, and one of the things we talked about in the last presentation about GMAW processes, we talked about arc blow, where there's a magnetic interference that pushes the arc over one place or another. Well, sometimes conditions like that will cause something called undercut. Sometimes it's a problem with the gas flow. Sometimes there's a bunch of other reasons why you might end up with undercut. But here's what I want to say. I want to say that undercut, my opinion, is the worst of all the problems that you could have with a weld. And here's the problem I have, and here's why I would define it like that. Because this weld is perfect. It's in the right place. It's at the right size. It's at the right length. Everything about it's perfect. If you had a welding machine that was sensitive enough that it could sense changes in the current or anything like that, and you said, hey, I got a quality check that can happen while welding is happening, it would have told you this weld is perfect, and it's way, way off perfect. There's a bunch of problems here that go along with the issue before we get down to what you're allowed. So we've put the weld in place. So much like that one picture, if you can remember that one picture where I said it was that plant in Mexico, and you could see the heat input from the weld had spread out and given us defined what we call tinting of the steel that showed us all the heat input in it. So as soon as this weld goes into place, that's what it does, especially if it's been put in place well and it has good penetration. It takes all the heat that's inside and it's going to start dumping it out into all these different places. When it dumps it out, it actually creates a softer structure. We heat treat these areas known as the heat affected zone, right? And we heat treat them when you get them hot, and then the volume of heat in this keeps coming. It keeps coming. And that's the recipe to soften material. When you keep a material hot, keep it hot, keep it hot, keep it hot, that ends up making this material softer. The grains grow, and that's not doing us any good, because this confined and small area, now this heat that's being dumped out is confined into a smaller area. Larger areas create heat sink. That is, they can absorb heat a lot better. This small area has to sit here, and it's going to stay hotter longer while the heat is trying to get through this area and spread itself out and conduct through the material. So now we've got a softer structure between here, and wait a minute, it gets even worse. Now we've got a notch in it, right? I don't think there's anybody that hasn't notched something, put a notch in something to make it easy to break. If you go walk around your plant, you'll see saw marks in the floor, in the concrete. These saw marks are there to define where these huge pads of concrete are going to crack, because they will crack. They will move. Well, if this is a dynamically loaded material, they don't want this happening, because this is going to be a softer area, and it may as well have a big sign on it going right there that says crack here. And the dynamically load, especially if in a structure, if it's part of the suspension or anything that's holding the suspension, right, it is going to be under any types of stresses. It's going to crack through. And this is a dangerous one too, because if you miss it, it's something that's going to happen in the field. And the only ones I've ever seen that have showed up very bad, they made it all the way to the field to the point where things were knocking. The customer brought something in that was knocking. When he pushed the brakes, it knocked. It was this weld, this material. It was a perfect weld, but this material had broken through like this, and it was giving us the problem. So there's a couple of quick rules here. Now, these should be done, more of a note to engineering and quality, but these should be done in a border sample. You should have some type of a sample there for the people to see, to give them a gauge, if you will, a visual gauge, if you will, about what's allowed and what's not allowed. I usually make up about, and if this is 20%, right, you could make a little bit of a visual gauge so they can see. It's 5 inches long, and there's 1 inch allowed for 20%. So there's some pretty simple ways to give people gauges to do this. Otherwise, if you do see an undercut starting to build, and there shouldn't hardly be any coming around. So if you do see undercut, though, you make sure your weld quality people are addressing it right off the bat, right? Here's a cross section of an undercut component where we've lost enough parts, or we've lost enough of the base metal that's cause for concern. These things are found in specification. Your responsibility is to take the information we give you by border sample or pictorial, or maybe even a gauge of some kind, and make a determination whether another weld goes into place. This is the good part about undercut. Much like an off-location weld, all it would take is the reprocess of a little bit of a weld right there, and it's good. Now, sorry, one thing I wanted to mention here. There's specifications where things are allowed and things aren't allowed. But I want to point this thing out. When specifications tell you that, and it's always better to go a little more. And I understand most people's belief that if I do more, and I'm always cautious of that, because sometimes you could do more harm than good. But going back to putting the weld in here, you're going to make that choice based on whether this meets the criteria. Now, that heat input, that extra heat input, could cause issues back here, but you have to meet that criteria. Now, not too many specs address the beginning and the end of a weld. In the beginning and the end of a weld, there needs to be some considerations. At the beginning and the end of the weld, I don't want, and this is a special, I'm going to call this a special Bob rule, and I'll tell you why I have it. I don't want any undercut at the beginning or the end 25 millimeters of a weld. And I'll say this because in destructive testing, I've seen the smallest amount of undercut just work its way right through the material in hardly any time whatsoever. So I'm always because it's had an opportunity to get it at the beginning, and then it just propagated through. Remember, I was talking about that heat affected zone that's a little softer, and it's propagated and run a crack all the way down right at the toe of the weld. So I'm always cautious about any form of undercut, even though it's not addressed in all spec. Any form of undercut at the beginning, or at the start or the last 25 millimeters. Please, let's not forget personal safety hazards. The shop, the phone call you don't want to get from a plant is that somebody's been injured by a part you sent them. It's going to be, it could be very serious. And believe me, I've had to go through this where we've had to go down and try to understand it. Now, none of these things were anything I investigated at the time, but I don't think there's anybody in here that, probably in this room, that hasn't seen something like this. You could be new enough that you haven't seen it, right? Or something like this. Now, these are serious. I'm going to tell you, this is a piece of wire stuck on here very good. And the wire probably came from a wire that was advancing, and it basically bumped off of something or broke off when it melted. But it spit the wire out, and we end up with these little pieces that will weld themselves to a part. Now, if you put your hand over that and squeeze, it's going to go through a glove if you're squeezing hard enough. Now, most of these people know where to look, and most people follow the rule. I'm never going to touch what I can't see. And that's a great rule, by the way, for safety. When you work in heavy industry, that's a rule you live by. So you have to be careful, and you have to look for things like this, and you're looking for these hazards. And don't just look at them for their reason. Think about yourself. You have to know these hazards do exist, and it should be part of a safety program when it comes to this. Now, the icicle drip, see this piece that's actually rolled off the edge and fallen down, and when it fell down the edge, when it fell straight, and then it cooled, and that's why it's pulled itself away, because when it cools, it shrinks. So it's pulled itself away. But see that? That is a razor blade, and it's a jagged razor blade. It will cut through anything, and it'll stick to a glove, and when you pull away, it'll slice you. And I don't want to get too graphic about it, but I've seen 2 accidents with situations like this, one in automotive, one in power generation, where there was and both of them were welding inspectors that were looking with their hands instead of looking with their eyes. And we have to be careful of this, and we have to make sure nobody gets hurt inside the plant, and we got to make sure nobody gets hurt our plant and their plant, right? And don't forget, under almost all conditions, there's an E-coat involved. So those people are playing around here too. And we're probably not going to get a very good E-coat unless we knock that off of there. Most people will take a grinder and grind that to make sure it's gone. The utmost of care to make sure that you don't thin the material on either sides of the weld, please. Now, this last little thing here was fit and function. This is one of the things that we're always, and there's always a few people in the plant when you have a component who have actually been there, seen the part, seen how it goes together, all the aspects of it. And they're the ones with the intimate knowledge that we need often when we're building the processes for you folks as reprocess welders. If you get a little bit too carried away with your reprocess weld, you might end up making a little bit of a melt through, right? Which is a little bit of a bump on the other side. Now, normally, these are the types of things that show up on notices later on, right? On station notices that say, there's a problem, we need to look at this. Because they had one go through, but you have to be considerate that there might be a part that has to mate to this part, right? Don't always think I got a little bit of melt through on the other side and it's okay. Do not wait for some quality bulletin to show up and put this up on the board because it made it to the plant if you see you're getting a lot of this melt through. That condition can cause some pretty serious problems. Sometimes there's allowances, sometimes there's not. You'd have to go to your OEM spec to understand this. But remember, it's not just a spec, it's fit and function, that's part of it. We need your attention on that. Thank you. Stops and starts. Not much to be said for stops and starts other than the start of the weld doesn't get tested for a few millimeters, and the end of the weld, which we know as the crater, which I'm going to talk about a little bit more here, is also not part of the inspected areas. And when I say inspected areas, I mean areas that go to quality and actually get cut into pieces to make sure you have a good sample. The start of the weld could be a little bit discrepant. The end of the weld could be very discrepant. There's only something special about the end of the weld that we need to discuss a little further. So, sorry about that. So at the end of the weld, I just want to say one thing. When they're defining what a weld should be, they'll say the weld should be as long, there should be enough weld here to meet the length that we are prescribing. What they've told us, we want this to be 200 millimeters long, and there has to be 200 millimeters of good weld. Now, there are specs out there, and almost all, that give you a little bit of movement in this area. That is, if you've got a little bit of discrepancy, and sometimes that's why they'll make a weld a little bit longer, it shouldn't make any difference. I do want to point out one important thing, though. The crater condition. This is the crater of a weld. This is the end of a weld. Now, even in steel, it's very important in aluminum and all these other, but even in steel, you can't use your welding process to damage the base metal. So your crater can't be sunk in. It can't be down too low. It can't have edges on it. If it looks like a bowl when you're done, it needs to be fixed. That is, it needs to have some fill. The part of the weld that's measured is the length of weld that meets the spec. That's how simple it is. However, again, with these ends, with the craters, you have to make sure those craters have not damaged the base metal. That is, left a crater that sinks down into the base metal. Whether it's a burn-through condition where we're starting to see a little bit of, or I should say a melt-through, where it's starting to sink a little bit, no matter what the conditions, we can't leave something that's going to be a clear defect in the material like that. Again, it's almost not in the weld. The welding process caused this to happen. And just a quick reflection back into making sure I want the beginning and the end of my weld to be excellent. Right? Most people pause long enough at the end of their weld, or most people that would learn welding learn to pause slightly at the end of a weld to make sure that the crater itself is filled. And it was like a broken record. Fill your crater, right? Well, the robots do this as well. They have things on them called crater fills, but under the conditions, sometimes it's very difficult to get a crater fill done. That is a whole new special course on all these setup parameters and how to, like the process of developing all these things and getting them all work together, how a weld starts, right down to extinguishing the arc and post-finishing the gas. Weld and or base metal cracking. Okay. Before I get into this too much, I want to make a point. There's no such thing as an acceptable crack. Everybody that would call me and tell me we have welds cracking, I don't care what industry you're in. It's a serious, serious thing because it can be metallurgical, it can be structural, it can be contaminations. There's a bunch of different things. So first thing, before I start talking about these, I want you to know that there's no such thing as an acceptable crack. And if you're standing there and you see one, your job is to stop making parts. And I know there's other people in this room, and hopefully from quality or who have seen this program, and from quality and engineering, and we're all saying to you right now, and I know there's no argument, if you see cracks, this is a 4-alarm issue. Now, what could be wrong? Well, let's go by wrong by going by what the problem is. So sometimes you can weld certain types of materials that give us all kinds of problems. Boron steels come to mind. There's they were also known as hot stamped. They have some metallurgical problems where the weld itself, that spike of heat, has caused hardness of materials. Sometimes, this is often what you see, this first one is often what you see in the field, but I've seen it occasionally when we're welding specialty metals where our welding process has either not been hot enough or we didn't use quite the right filler metal we should have, and we've caused some embrittlement right in the heat affected zone. Now, the first thing I want you to know about this is, remember one of the rules I said before, you can't put weld metal where weld metal is not supposed to be. This is a weld that's, and if they've told you that that's a 3 millimeter fillet or a 4 millimeter fillet, and you've got to start coming out here, way out here, right? That's a stop, right? That's a stop. You're putting weld metal where weld metal was not supposed to be at this point. The base metal has been compromised outside of where the weld's supposed to be. That's junk, right? Don't even give that one a second thought. Now, this one, transverse cracking. Now, transverse cracking usually happens as a result of a condition called hydrogen embrittlement. You might remember from some of the previous programs where I've said that hydrogen is our worst enemy, and silicon is our favorite element because silicon mops up all those impurities, does some great things. Hydrogen forces that condition called hydrogen embrittlement. And you see welds that look like this. Now, often, these welds extend into the base metals. Often they do. If these cracks do extend into the base metal, that part would be junk. Because now, again, we got to start putting weld out where weld is not supposed to be. So, I'll give you an example of transverse cracking. I'll give you an example of the condition where I've seen it in automotive. So I was in a plant in Chatham about 10 years ago or so, and it had been really, really cool. Cool enough that all the plant doors were open, but for the last 3 or 4 days it had been down about 50, 60, and it was kind of off and on, but everything in the plant, my point was everything in the plant was cool, including these great big reels of wire, 1,000-pound reels of wire. And then very quickly, one morning we got up and this hot, humid weather had come in. And I never thought anything of it. I was down there working in the plant, and I never thought anything of it at the time. I wasn't even on this project. It had nothing to do with it. But I walked out of the hotel. They had just built that Holiday Inn in Chatham, and I walked out, and it was it was so humid out that the hotel wall where the windows were, where the air conditioning was on, was actually wet with water. And I never thought too much about it. And it was actually running down the building and condensating, which is standardly what happens. The same reason you take a cold can of pop out in humidity or a can of beer or whatever, and it starts to develop all kinds of water. Well, I get to the plant, and they start showing me that they're seeing these cracks. And I'll be honest with you, I was a little bit bewildered at the start because I'd never seen it happening under these conditions. And some things have been changed recently, so we were looking at that. But at the end of the day, I walk over to the reel, and I took my hand and I just rubbed my hand, and there was like a fog. There was like a little moisture that had built up on the cold steel. The steel was cold through. It was nice and cool. But as soon as the humidity came in, the humidity condensated on the wire. Speaks volumes for having drums of wire. That's why a lot of companies have got away from having these big reels. Now, longitudinal cracks are a different type of crack. And there are, at the discretion of your quality department, opportunities here to repair these if they're related to a crack that I'm going to show you in another picture. But sometimes longitudinal cracks happen as a result of fixturing issues. If the fixture holds the part too tightly, when the weld goes in place, the weld immediately starts to cool when you're done. And when it starts to cool, then it starts to shrink. And when it starts to shrink, If it shrinks too much, if the weld's too heavy and it's too thick or whatever, it'll start pulling, and it'll actually pull itself apart. It'll pull itself apart in the last spot to cool down, right down the center of the weld, right? Because the base metals themselves are pulling the heat out. So as an example of a downhand crack, now this is happening because the person's going so slow, or they're using too much heat. You have to be careful doing downhand welds. And people, they love downhand welds. I can put in a beautiful weld downhand, but it holds nothing. So downhand welding is almost unheard of in any form of structural welding and professional welding where you hold a ticket. And the procedures are few and far between. A few gas procedures, and there's a couple of tickets you can hold for downhand in 7018. But the gas metal arc welding process doesn't like this. And what you'll do is you'll create a very thin weld where the puddle will start to run ahead of you. Pulse can help out with these, and developing a welding schedule that can do this is a little bit tricky, but it can be done. Now, just before I carry on, this particular weld, I'm looking at it and I'm thinking to myself, if a person could get a grinder in there, I'm only saying this because it would again be at your discretion of your quality, but there's nothing contaminated about the material. Their problems do not extend into or outside of the toes of the weld, so the weld is intact. There's no metallurgical issues with it from a contamination point of view. I don't see anything. So if you could get a grinder in there, grind some of that material away so we're not worried about the compromise in penetration, open it up, and replace that weld. Again, quality is discretion. But I would consider it. We already talked about location, cracking. We talked about how I do not like crater cracks or anything like that either. Excessive spatter. Okay. Now, before I get too excited on spatter, there's a couple things I want to say about it. But the first thing is, customers don't like spatter because spatter affects the integrity of E-coat. If this thing's got to go out and get E-coated, they don't want it to look like that. Now, that's a pretty bad one. It happens to be up there in the picture to illustrate it. But that's why some of the specs have limitations. And they create spatter-free zones that can't have any spatter. They can't tell us no spatter at all. They can only tell us we want these areas to have no spatter at all. So if there's any type of problem. Now, most nice, clean materials, if it happens to be non-coated steel, you should hardly have any spatter whatsoever. If you do have spatter, there's something else dreadfully wrong. Whether it's the gas or the choices or the electrode or filler metal, there's something else going on. So they don't like it because of that. Now, one of the reasons I want you as the welding inspectors to pay attention to this is shielding gas is part of our process. We've talked about it before. I'm thinking at this point you will have seen the process version of these presentations, so you understand the 7 purposes for shielding gas. But when shielding gases get out of balance, you guys are the first person to see it. You guys will start to see changes in the weld. So, here was a scenario. I want to tell you the story, and I want you to think about this story when you start seeing spatter start to develop, because it'll happen slow. Remember, it'll always happen slow. So a few years ago, I got a call on a Sunday afternoon that we had a plant that was having struggles with spatter. So they called me and they said, "We've got spatter." I said, "Okay, how bad?" So he sent me a picture, and I went, "That's bad." And I said, so stop that cell. He goes, "We got to stop the whole plant." I said, "Then stop the whole plant. I'll be there in an hour." And I drove to the plant, and they had to put the lines down. There was spatter everywhere. So what had happened was, They mix their gas in this plant. And we talked in that presentation about mixing argon and carbon dioxide. So we have this argon and carbon dioxide. Argon promotes spray transfer. Carbon dioxide promotes what we call a short circuit. It's a more of a harsh weld that has a lot of spatter. And when I drove up and I walked up to it, and the first thing I did, I drove right to the plant and drove right up to the mixer. And I walked out to the mixer, and sure enough, the argon had a valve failure, and the safety had shut the gas off, and all the lines inside the plant over the last few hours had filled up with carbon dioxide. Now, it made a lot of spatter. Was it acceptable spatter turned into a big question. At the end of the day, there were a lot of areas that it was not acceptable, and we had to do a little bit of light buffing, right, sanding, if you will, being careful not to take the spatter off. We had to get some special permission, but basically we had about 16 racks of parts that had gradually become worse and worse and worse, to the point where the spatter didn't look too much different from this all over the plant. Now, here's the point I want to make to everybody right now. Everybody in the plant saw this problem. Everybody in the plant, when I investigated, everybody in the plant identified it as an issue, and nobody communicated. Nobody said, "Are you seeing problems over here?" And that's all it would have taken. Some of these people were like 10 feet apart, and they didn't communicate these changes. And here's what I'm going to ask of you. I'm going to ask you, when you see changes like this happening, say something. Because 10 of those racks that we made that day, we had to throw away. They were so far out of spec for the gas, for the penetration. There was no way to, we did cross-section. It changed the penetration profile. I tried my best to make sure that they would take those parts no matter what I did. And in the end, they just went back, pointed at the spec, and said they're out of spec. Sorry. And they all went into CAM. So there's a lot more to it, a lot more to having spatter. And I mean, I only touched on a little bit before about the importance of spatter-free zones. This is where you have something that's going to be rubbing on that zone, probably a piece of rubber of some kind. And if there's spatter underneath it, that little piece of spatter will start wearing a hole. And you don't want anything. We want to do everything we can to make sure we're not interfering with the E-coat later on. And having spatter-free or a very controlled spatter makes life a lot better. So that concludes the presentation when it comes to the quality. If you have any questions and so forth, you could always give me a call. There's my email address and my cell phone number. Please let me know. I hope you enjoyed the time, and please let me know if there's anything else I can do for you. Thank you very much.